As Nicholas Copernicus presented the heliocentric model, one more emotional modification of how we might interpret the universe occurred, prompting a debate known as the enormous emergency. This issue is described by enormous contrasts in our estimations and comprehension of the fundamental qualities of the universe, like its age, size, and speed of development. According to Neil deGrasse Tyson, the discovery of the James Webb Space Telescope, JWST, brought an image that defies physics to an end to the
Delta
debate.
rocket carrying
Be that
Blast,
as it may, what is
gamma-ray
this issue
telescope
and how could the
searching
James
for
Webb
unseen
Space
physics
Telescope help?
in the stars
Because
of
the
the
review
galaxy.
is still ongoing, the assistance is somewhat overrated. The crisis is the point at which our understanding of the universe is challenged, particularly in terms of its age and size, which are significantly linked. The presentation of the JWST has been essential in this specific situation. We were limited in our ability to see into the early universe before this breakthrough. Be that as it may, with JWST's superior abilities, space experts can investigate substantially more far-off cosmic systems, giving us new viewpoints on the universe and testing a portion of our past originations. This progression permits us to peer further back in time, nearer to the enormous detonation, and notice worlds as they were framing, giving basic information that can either support or challenge our current models of the universe. To comprehend the emergency exhaustively, it is essential to audit the standard model of cosmology, known as the hot inflationary enormous detonation model or lambda cold dull matter lambda CDM model. This model is fruitful in making sense of the peculiarities of the universe, from the astronomical web to the development of cosmic systems. The lambda CDM model proposes that the universe began with an enormous detonation, trailed by a time of fast expansion and proceeded with development. Dark matter, which attracts matter, and dark energy, which drives the universe's rapid expansion, are two examples of its components. However, every new observation, particularly from sophisticated instruments like JWST, raises the possibility that our existing model is incorrect or needs to be altered. The lambda CDM model makes forecasts about the properties and conduct of cosmic systems at various phases of the universe's set of experiences. For instance, it is anticipated that galaxies will be smaller, denser, and more abundant in heavy matter than the local universe. This is due to the lengthy production and distribution of heavy elements in star cores via processes like supernova explosions. In hindsight, galaxies ought to be less dense, bluer, smaller, and richer in heavy matter. This leads us to ponder times of existence without apparent stars or heavenly bodies. However, scientists have discovered contradictory evidence that casts doubt on these forecasts. Uncertainty regarding the universe's age is the root cause of the problem. It can be challenging for scientists to reconcile the varying results of various measurement techniques. Scientists employ a variety of techniques to determine the universe's age in order to resolve this issue. One strategy includes concentrating on the inestimable microwave foundation, CMB, radiation, and looking for the historical backdrop of the universe's extension utilizing numerical models, like Friedmann's conditions, in view of Einstein's hypothesis of relativity. The CMB, left over from the beginning of the universe, is an essential device for this estimation. The structure of the universe can be better understood with the help of comprehensive maps of the CMB, such as those produced by the Planck mission of the European Space Agency. Dark energy, a significant part of the universe, is only partially covered by these maps. Researchers utilize Friedmann's conditions and different perceptions to assess the pace of development of the universe and decide its age. Observing exploding stars, particularly type Ia supernovae, which are used as standard candles due to their constant luminosity, is another approach. Astronomers can determine the distance between these supernovae and the rate of expansion of the universe at various times by comparing observations of them. Dark energy was discovered using this method, which is now essential for universe measurements. Since the Big Bang, which occurred approximately 13.8 billion years ago, the universe's expansion has been measured by the Hubble constant. NASA has noted critical ramifications in light of this study. A sluggish development could propose some obscure power, while a quick extension could show the presence of dull energy. In January 2018, specialists found a fascinating disparity. The Hubble Space Telescope estimated a quicker extension rate in the close-by universe, while the Planck telescope recorded a more slow development rate at the universe's far comes to. This distinction features the immeasurability of the universe and reviews Edwin Hubble's spearheading work in 1929. One of the pillars of modern cosmology is the discovery by Hubble that distant stars were moving away from us, indicating that the universe is expanding. We have refined our measurements and investigated additional variables as technology has progressed, including the Hubble and JWST. In spite of these headways, the discussion proceeds, especially between estimations in light of supernovae and CMB readings. Since the revelation of dull energy in the 20th years, researchers have been perplexed by errors in the universe's age and development rate. As estimation innovation turns out to be more precise, little changes happen, prompting more inquiries. In a universe that is 13.77 billion years old, even though these differences are only 10 to 20 million years apart, they still require investigation. A potential clarification for this disparity is a blunder in CMB estimations, which have been totally tried since the Planck mission's send-off in 2013. Another viewpoint proposes holes in how we might interpret dull matter, which might change after some time and be impacted by dim energy or other obscure elements. Due to the complexity of stellar explosions, which introduces uncertainty into our models, the precision of supernova measurements is also questioned. Settling these vulnerabilities in cosmic explosion models will assist with making sense of disparities in estimations. The issue in the universe was escalated by the revelation of the James Webb Space Telescope. As per Neil deGrasse Tyson, JWST has uncovered infinite items that challenge our ongoing figuring out, showing that our logical seeing requirements a total upgrade. In any case, the issue is that we don't yet have any idea where to begin. We must examine the early universe 150 million years after the Big Bang, when stars, black holes, and star clusters began to form, in order to comprehend the scope of this scientific apocalypse. Ongoing JWST pictures show cosmic systems that are significantly more far off and, accordingly, more seasoned than momentum universe models foresee. Our model needs to be completely reworked because of this discrepancy. The disclosure that the universe relies upon systems is new. JWST pictures show worlds that framed sooner than our ongoing models anticipate, causing huge difficulties in the field. This issue influences worlds with redshift, a typical estimation in cosmology. As indicated by the Standard Model, hydrogen started to show up around 400,000 years after the huge explosion, prompting the development of the primary stars and, at last, worlds. The formation of galaxies depends on these early stars' production of heavier elements. The course of world arrangement and advancement is perplexing, including the converging of more modest designs and the consistent development of new stars. However, the fact that JWST has discovered galaxies that formed much earlier than anticipated suggests that our understanding of the early universe needs to be revised.